In this video, we will learn how to find out the extremum of the given function. The question is, find the extremum of u is equal to x square plus y square plus z square subject to x plus y plus z is equal to 1. Okay, we need to find out the optimal values of x, y and z for the given function. Okay, so we will be using the Lagrangian method here. So first thing is what we do to solve this question. So we form the Lagrangian method, Lagrangian function. Okay, so for that what will we do? We take this budget constant first and set it equal to 0. That is, if I set it equal to 0, I will get 1 minus x minus y minus z is equal to 0. Then what will I do? We will multiply this both sides by lambda. Okay, then we can form the Lagrangian function, that is L is equal to, so Lagrangian form is equal to the objective function. So this utility function is called the objective function, and to this we add the resulting constraint here. We don't have the budget constraint here, so we have the general constraint. So we have this x square plus y square plus z square. To this we add this constraint that we formed, that is lambda times 1 minus x minus y minus z. This is our Lagrangian function. Okay, since we need to find out the optimum or extreme values, what will we do? We to find out the optimal values of x, y and z, we partially differentiate this Lagrangian function with respect to x, y, z and lambda and set them equal to 0 simultaneously. Okay, so that means, and if I write it here, okay, so to find optimum values, we differentiate this Lagrangian function. We differentiate partially the Lagrangian function with respect to x, y, z and lambda and set them equal to set them equal to 0. Okay, then we can find out. So let us find out. So L subscript x means the partial derivative of this Lagrangian function with respect to x. Derivative of x square will be 2x and derivative of y square is 0, z square is 0 because we are taking the partials. Now in this case derivative of x is minus 1, so we have minus 1 times lambda is minus lambda and we set it equal to 0. Likewise we take L subscript y, that is the partial derivative of this Lagrangian function with respect to y. So we will get 2y minus lambda is equal to 0. Okay, similarly L subscript z means 2z minus lambda is equal to 0, and L subscript lambda means the derivative of this function with respect to lambda. Since no lambda is involved in the first three terms, derivative of lambda is 1, so we are left with 1 minus x minus y minus z is equal to 0. Okay, so can we rewrite these equations here? So can I write 2x is equal to lambda? Okay, and here can I write 2y is equal to lambda, and here 2z is equal to lambda. Let us say this is equation first, equation second, equation third. Okay, so here you can see since RHS of each equation is same, we can equate LHS. This is to say, if we have x is equal to 5, y is equal to 5, z is equal to 5, can we say x is equal to y is equal to z? Yes, we can say. Since we have the same RHS, we can equate the LHS. That implies 2x is equal to 2y is equal to 2z. Okay, so dividing each by 2, so we get x is equal to y is equal to z. Okay, now what will we do? Let us say this is equation 4. So let us put x is equal to y and x is equal to z. Okay, x is equal to y and x is equal to z in this equation. That means 1 minus x. In place of y we write x again, and in place of z we write x again, because x is equal to y is equal to z, and which is equal to 0. So put these x's on this side, or let me first write it. So we have minus x minus x minus x, so this is minus 3x is equal to 0, or 3x, if I transpose it, is equal to 1, or x will be equal to 1 upon 3. So this is the optimal value of x. Now since we know x is equal to y is equal to z, that means y bar will be equal to, or y star, or optimal value of y is 1 upon 3 again, and z is also equal to 1 upon 3. That means x, y, z will be equal to 1 upon 3, 1 upon 3, and 1 upon 3. This is how do we find out the optimal values of a function. I hope I make myself clear in this video. Thank you.